Today we want to run a very popular example in Lagrange multipliers where we're optimizing some objective subject to some constraints. So in this example, we want to optimize the function f of xy equals x to the 2/3, y to the 1/3 subject to 10x plus 4y equals 60. So this is actually just lifted from, this is the Cobb-Douglas production equation. X is units of labor and y is units of like materials or something like that. The constraint would be our budget. We have 60 units of money to work with. Each unit of labor costs 10. Each X unit of labor costs 10. Each Y unit of, say, materials costs 4. And so if I have a 60, this is how I can distribute my units of labor and material. I can't remember what the other stuff. Now, this is an interesting equation. The idea here is that we have a product of a power of x and a power of y. And the exponents add up to 1. So the form is x to the alpha, y to the 1 minus alpha. This is how you'll see this a lot. So it'd be like, if it was like x to the 3/4, it would be times y to the 1/4, or x to the 1/2 times y to the 1/2. Those ones add up to 1. The interesting thing about this, when we have, we're saying that x and y are inversely proportional. We would say y is inversely proportional to some power of x. That's what's going on in this equation. So from a math standpoint, this equation, x to the 2/3, y to the 1/3, what's going to happen in this is that the level curves, we'll be able to say y is inversely proportional, in this case, to the square of x. Generally, this is what's going to happen when you have this kind of setup. It'll be inversely proportional to some power of x. If we look at a level curve of this function that we're optimizing, we could say x to the 2/3, y to the 1/3 is equal to some constant. So there's a level curve. If I solve this for y, you see we have to divide by the x. So I have y to the 1/3 is equal to k over x to the 2/3. Then if I want to get y by itself, I'll just raise both sides to the 3rd power, not the 1/3 power, to the 3. So that'll give us y is equal to some other constant. I actually have this lowercase k to the 3rd power, but it's just some constant, so I don't really care. I'm just going to give it a different name. It's just a constant of proportionality. I'm not worried too much about it. Like, oh, that's kind of concerning, the lowercase k and uppercase k when you're writing stuff down. Aren't you worried about that? I'm like, oh, no, it's an arbitrary constant. It's just a constant of proportionality. That's not the interesting thing, what's going on. When I say the function is x to the 2/3, y to the 1/3, we're saying that these two variables are inversely proportional. Or in this case, y is inversely proportional to the square of x. When we have two variables where if one variable is inversely proportional to a power of another variable, we'll have a predictable looking level curve. we see that as x goes off towards infinity, then y will drop down to 0. And then as x gets closer to 0, y goes up to infinity. So our level curves will all look like variations of like a 1 over x function. So our level curves will all be variations of this inverse proportion. Since I'm drawing this kind of sketchy, this can represent the level curves for all these kinds of functions. Where we get an x to the alpha, I think x to the beta times y to the 1 minus beta. When we have the product of variables equaling some constant, there's going to be an inverse proportional relationship. Inverse proportional means if we double one, then we cut the other one in half. Because it's a product, not with these powers, but if it's just x times y, if I double x, I have to cut y in half to maintain balance. Where we see something like this, where y is proportional to, the inversely proportional to the square of x, that would be something like gravity. When we're twice as far away, we don't see half the gravity, we see a quarter of the gravity. I don't know if we see the gravity, experience the gravity. That's physics thing. Any questions? This is probably want to work on. We want to apply Lagrange multipliers to optimize 2x to the 2/3, y to the 1/3 subject to 10x plus 4y equals 60. Take a moment and start running through these calculations, see if you can get through them. If you get stuck, we're about to break into groups, and then you can discuss it with your classmates.
What is the alpha?
This is just the generic form, where I have alpha and then x to the beta times y to the 1 minus beta. All right, take a few minutes, think about this, try to run through the calculations. Today is the day we practice calculations. Tuesday was like, oh, here's the problem. Bye. Wednesday was like, oh, here's how we're going to think about the problem. And then Thursday is, here's how we're going to actually do the problem. So do the problem. We all had the calculus part of the problem. The calculus part of the problem is make the gradients go in the same direction. Find the partial derivatives, make them equal to each other, go in the same direction with the lambdas. What we end up with is a system of 3 equations in 3 unknowns. One from the partial with respect to x, one from the partial with respect to y, one from the constraints. This is where the problem is tricky. I recommend if you're going to practice solving this, use the first 2 equations to eliminate lambda. Solve for lambda in both these equations, and then say lambda have to equal lambda. And then that'll give you an x and y that you can plug into the second equation. All right, that's going to do it for today. 3 things need to happen. Caps back on pen, pen back in tray, cards on the front table. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.